Okay, so we'll continue on, and the last piece in terms of correlation regression is a regression. I have an example on the next slide. Just some data. I have 1, 2, 3, 4, 5 subjects. I've measured them on some variable x, which is on the x-axis, and variable y, which is on the y-axis. I can see I've calculated the correlation coefficient for the sample correlation, and I can see that the correlation is plus 0.64. This means that the trend is up in a positive direction. The higher the values of variable x, the higher the values of variable y. It's not a correlation coefficient of 1.00, which would be perfect, and all the dots, or those little diamonds on the scatter plot, would all fit on a straight line. They don't. So there's that line, which that line is referred to as the best fitting line. And I can see how the points don't all fit on that line, and the further they spread from that line, the lower the correlation becomes. That line's important, and there is a special couple of formulae to use to calculate that line, and it's referred to as the line of best fit. And the location of that line minimizes the distance squared between a point, the y value for a given, say if I have this value here, the best fitting line reduces the distance between the diamond and, if you go straight down, where it would touch the line. So that distance between the line and the diamond, that distance squared, is the least it can possibly be for that line. So what I need to do is I need to determine the slope, the equation for that line. And in a Cartesian two-dimensional plane, how to define that line in a two-dimensional plane, I need to know what the slope of the line is for every unit of x. How many units of y does the value of y change? So if I go over 1 unit of x, how many units of y do I go up? And a is the y-intercept. That's where the line crosses the y-axis. So having those two pieces of information allows me to define that straight line, which is the best fitting line. The slope of that line for the data given here is the correlation coefficient between the two variables multiplied by the standard deviation of y over the standard deviation of x. So in this case, it's 0.639 times by 7.18 over 7.91. The slope function is 0.58. So for every unit of x I go over 0.5. I go up 0.58 units of y. So go from from 1 unit to the next on the x-axis. I increment up 1 unit of x, means I go up 0.58 units of y. That's the slope. The y-intercept is simply the mean of y minus the slope between the slope for the equation, which is the 0.58 from the previous slide, multiplied by the mean of x. Now, why do I use the mean of y and the mean of x and the mean of y? Well, because the best fitting line, one point on any best fitting line, is the point defined by the mean of x, mean of y. So a point on that line is mx, my. So all I have to do is simply solve for a in that equation using as my x value the mean of x, which is 20, and the mean of y, which is 27. And that gives me a y-intercept of 15.4. So the best fitting line crosses the y-axis at 15.4. Okay. So one final piece, sometimes you'll see in regression, we'll run a regression analysis in SPSS. We'll see what's referred to as the standardized values. They're referred to, for the slope is referred to beta, and then basically I guess you can call it alpha for the y-intercept. And if I use the z-scores in the regression model, so what I'm doing is I'm using the z of x and the z of y in place of variable x and variable y. The standard deviation for the z of y is 1. The standard deviation for the z of x is 1. That means for if I use the z-scores, the slope function is actually the correlation coefficient. And because the best fitting line of, even if I'm using the z-scores, is must go through that line has to cross the mean of x and the mean of y. For standardized scores, the mean is always 0. So therefore, the y-intercept is 0 because the line has to go through the point 0, 0. You'll sometimes see standardized slope functions, or a regression line that has the standardized functions, but that's more for next semester. So I'm just introducing it now to let you know what it is. So just to go back, my final equation is here. Here it's going to be the slope function is 0.58x, and the y-intercept is 15.4. So what I'm going to do now is I'm just going to walk through in Excel the calculation. So I'll grab my data. Well, let's do it for the food data. I'm going to do it for the food data. Okay, so I have my means. I need the correlation coefficient between, so I'm going to call food, this is variable x, and restaurant is variable y. So there's my x and y. I'm getting there. So I need the r, my correlation coefficient, and it is equal to, I'll use the Excel function, correlation between x and y. And we know it's our 0.988. Now, the slope function, so slope, I'll call it b. It's equal to the correlation coefficient multiplied by the standard deviation of y divided by the standard deviation of x. So there's my slope function, or my slope function. And I need my a. And it is equal to the mean of y minus the slope function multiplied by the mean of x. So the best fitting line y equals 0.655 minus 2.749. I can see that if I add this, if I calculate, if I do my insert my scatter plot. There it is. Oh, I don't want that. Let's. And actually, I'll put it on its own sheet. Move chart. Okay, I'll just leave the dots the way they are, and I'll just keep everything, title and stuff. I'm not going to fix up, but you can sort that out. Scatter plot. I can add my x-axis title, primary horizontal. And I'll add my primary vertical. That's not good. Okay, if I want to put my best fitting line on, I can go to add chart element, trend line. I'll add more trend options. I want to go more. So I want linear, and I can also display the equation. So this will replicate what we've seen. And there is our equation. I can make that bigger. And that should replicate what we did over here. Slope is 0.655. And the y-intercept is minus 2.7488. There we go. And that is how we calculate the regression line. We can do this in SPSS. I'm just going to do a copy over. So you can enter it in, control copy. Let's go open up my SPSS. Okay, I'm just going to paste it in. I can just paste in the values. And that's, let's call this person. And I'll call it food store and restaurant. Okay. So I want to complete my regression analysis. Okay, here we go. Regression linear. My dependent measure is restaurant, so I'm putting it as food store is my x variable. The x is the independent, y is the dependent, and then I run my regression. It should replicate what we have in and there we do it. There we go. Here's our slope functions. And I can pop that in to compare it to what I have in Excel. Not looking the prettiest. Oh, it's not. Let's just leave it. There we go. There's my food. Here's my slope. So that's my B. And my constant is my A. So here's my 0.655. Replicates what we have here. And my 2.749. There. Standardize, it gives you the beta, which is based upon the z-scores. And I know that the y-intercept is 0 and the slope function is the correlation coefficient, which is the 0.98. I can highlight that. And there we go. Okay, so that covers us for this week for our new material.